In the 10th lecture, we will cover the hypothesis testing when we have two samples instead of one. Previously, we have only one sample and test if a parameter is equal to a set value. Now, we try to test multiple samples and find if a parameter in one population is equal to that in another population as two-tailed test, or if a parameter in one population is more or less than that in another population as one-tailed test. Let's begin with two sample tests. For example, we may be interested to find if the boy's height is larger than the girl's height at a certain age as a one-tailed test. To compare two samples, first we need to determine if the two samples are dependent. Two samples are dependent if the subjects of one sample is related to the subjects of the other sample. Normally, we should be able to determine the dependence from the research question. For example, we would like to find if the father's average height is the same as their adult son's average height, or if the average left eye vision is the same as the average right eye vision, or if a medicine makes a patient lose weight. We measure patient weights at two different times, before and after they take the medicine. The first dependence is caused by the genetic connection between the father and the son. The second dependence is due to the fact that both eyes are organs of one individual. The last one is because the patient weights at different times should be related. When we have dependent samples, we cannot merge them into one sample because the combined sample is no longer independent and thus a random sample. If we have two dependent samples, we may use the paired t-test. The paired t-test matches the observations in two samples and forms a random sample using the differences within the pairs. The null hypothesis would be the population difference D is 0, and the alternative hypothesis would be the population difference is not 0. Basically, we use the difference between two samples to generate a new random sample and conduct the test as we learned previously. More commonly, we don't have an obvious reason to suggest the samples are dependent. Then we have two independent samples. Let's say sample A has N1 observation and sample B has N2 observations. The null hypothesis is mu A is equal to mu B, and the alternative hypothesis is mu A is not equal to mu B. When we assume that the two population variance are equal, we have a pooled two-sample test. Under these assumptions, the null distribution is a t-distribution with n1 plus n2 minus 2 degrees of freedom. The test statistic is t-statistic, which is y bar A minus y bar B divided by the pooled standard error SEP, which is determined by SP. Here, SP is the pooled sample standard deviation, expressed as this, where S1 is the sample A standard deviation and S2 is the sample B standard deviation. If the two population variances are not equal, it is more complex. The null distribution is t-distribution with new degrees of freedom. Here, nu is calculated using the Welch-Satterthwaite equation. We don't need to remember these, but the concept helps to understand the results in the next slide. This slide gives the example of the two-sample test. We use SAS software to conduct the test. We take two samples, 1 and 2, from boys and girls in a school exam, respectively. The sample size is 20, and the data is not real. Using the same data, we compare the results of both dependent and independent tests. In the paired test design, we match one boy in sample 1 and one girl in sample 2 to form 20 study pairs. We let each pair study together and help each other. Then we take the exam and we know the score is normally distributed from the past experience. We would like to know if the boys perform differently from the girls. The design makes the two samples dependent because the two students in one pair study together. Thus, it is a paired t-test. The left table is the SAS dataset. The first column is 20 exam scores from sample 1, and the second column is 20 scores from sample 2. The difference is sample 1 minus sample 2. The sample size is 20, and the average difference is 5.85. The null distribution is a t-distribution with 19 degrees of freedom. The test statistic is 12.26, and the p-value is less than 0.0001. The absolute sign here suggests that the test is two-tailed. The result is highly significant. We have enough evidence to conclude that the boys perform differently from the girls in the exam. In the independent two-sample test design, we don't form study pairs. We have the same exam scores, but the two samples are independent. In this case, we should use the independent two-sample t-test, and the results are shown here at the right. Instead of testing the difference, we directly test the equality of two means. Both samples have 20 observations. We have two methods, pooled t-test for equal variance and Welch-Satterthwaite t-test for unequal variance. The folded f-test in the last table tests if the two population variances are equal. Since the p-value in the f-test is close to 1, we find no evidence to reject the equal variance. Also, the degrees of freedom for unequal variance is 38, the same as in the pooled method. This infers that the assumption that the two populations have equal variance is valid. In practice, if we find that the results of the two tests are significantly different, then it suggests the two population variances are not equal. Here, both tests give the same results. The test statistic is 2.12 and the p-value is 0.041. At the 5% significance level, there is enough evidence to conclude that the boys and the girls have different exam scores. Compare the results between the paired t-test and the independent two-sample t-test. We find that both the test statistics and the p-values are quite different. The dependence between the samples may greatly affect the results even with the same data. Generally, the paired t-test is more powerful because it eliminates variation between the two samples. For example, the boy and the girl in the study pair spent similar study time. Thus, we don't have large variation in the study time between the two samples. However, the study time may vary between the girls and the girls when they are independent. Now let's start power analysis for two-sample tests. First, we need to introduce the practical significance. Practical significance quantifies the significance of the parameter difference in the real world. Statistical difference doesn't mean the practical significance. For example, we randomly choose 20,000 male adults from North Carolina and New York states respectively and measure their heights. The average height in the North Carolina sample A is 70 inches, and the average height in the New York sample B is 69.9 inches. We know the population standard deviations are 3 inches in both states. We use the pooled test, and the pooled standard deviation is also 3 inches, since N1 and N2 are equal. We find the test statistic z-score is 79 minus 69.9 divided by 0.03 is 3.33. And the p-value is 0.00087 for the two-tailed test. The difference is statistically significant, but a 0.1 inch difference could be within the measurement accuracy. It may not be practically significant and helpful in decision making. Cohen's d effect size is an appropriate effect size for the comparison between two means. Mathematically, it is the difference of the sample mean divided by the pooled standard deviation. If d is less than 0.2, then the effect size is small. If d is around 0.5, then the effect size is medium. If d is greater than 0.8, then the effect size is large. And if d is greater than 2, then the effect size is huge. The greater the effect size, the greater the difference will be. The last example has a d of 0.033, which suggests the effect size is small and the difference may be trivial. In the last lecture, we learned how to calculate the power of the test when we have one sample. And now let's do the power analysis when we have two samples. If two samples are dependent, then we generate a new sample using the difference, and we have one sample again. Now let's see when we have two independent samples. Previously, we learned how to calculate the power analytically. In practice, we often use the software to do the calculation. Here we use SAS and R. In SAS, we may use proc power to conduct a power analysis. We use the example in the last slide. The two samples each have 20 observations. The sample mean are 80.55 and 74.7. The pooled sample standard deviation SP is 8.7346. We may have all these numbers from the results in the last slide. To calculate the power, we put a dot in the power line, since the dot means missing. If we need to calculate the minimum sample size required for a specific power, such as 0.8, then we should replace 20 with a dot and also use power equal to 0.8 instead. In R, we first include a library, PWR, and use the function pwr.t.test in the library. The parameter D is Cohen's d effect size, which is 80.55 minus 74.7 divided by 8.7346. The calculated power is 0.542. And the minimum sample size required for the power of 0.8 is 36 for each sample. The power of the test is quite low for independent samples, while it is very high if the two samples are dependent. In summary, we learned two-sample hypothesis tests to compare two samples from two populations. First, we need to determine if the two samples are dependent from the research question. If we have two dependent samples, we may use the paired t-test. The paired t-test matches observations in two samples and forms a new sample using the differences in the pairs. The null hypothesis is the difference is zero, and the alternative hypothesis is the difference is not zero. If the two samples are independent, then we use the pooled two-sample test if we assume the population standard deviations are equal, and the Welch's test if we assume the population standard deviations are not equal. The dependence between the samples may greatly affect the results even with the same data. Generally, the paired t-test is more powerful because it eliminates variation between the two samples. Sometimes statistical significance alone may not quantify the size of the difference. Effect size offers a numerical measure of the practical significance. The greater the effect size, the greater the difference will be. Cohen's d effect size is the sample mean difference divided by the pooled standard deviation. Cohen's d effect size may be directly used in a power analysis.